Okay, sample problem 1.7. An empty container with a volume of 9.850 times 10 to the 2 centimeters cubed is weighed and found to have a mass of 124.6 grams. The container is filled with a gas and reweighed. The mass of the container and the gas is 126.5 grams. Determine the density of the gas to the appropriate number of significant figures. Okay, so this is a real type of issue. Here's what we're doing. We're saying, look, we've got this container. And when it's empty, the mass is 124.6 grams. Then what we're going to do is we're going to fill it up with a gas. Now, when you fill this container up with a gas, what do you think will happen to the mass? Will it get larger? Will it get smaller? Will it stay the same? As far as we know, there's no such thing as negative mass, as far as we know. Substances have mass, so the mass should go up. And if you take a look at it, it did, right? It went up by actually almost 2 grams. It went up by 1.9 grams there. So from that, we would conclude that the mass of the gas that you filled it up with would be the difference. It would be the combination of the gas in the container minus the container itself. Does that make sense? If you weigh something empty and then you add something to it, think of it this way. You weigh a car, it weighs 2,000 pounds. You put 4 people in, it weighs 2,800 pounds. The weight of the people would be the 2,800 pounds minus the 2,000 pounds, or 800 pounds. That's essentially what you're doing. Okay? So the mass of the gas is 1.9 grams. It tells us the volume of the container. 9.850 times 10 to the 2 centimeters cubed. Okay? So now we have the volume, we have the mass. Let's calculate the density. Remember, density is mass over volume. So 1.9 grams over 9.850 times 10 to the 2 centimeters cubed. Now, let's go through this on a calculator. 1.9 divided by 9.850 times 10 to the 2. 9.850 times 10 to the 2. See how I entered that in? I'm going to show it to you again. 1.9 divided by 9.850 EE times 10 to the 2. And there you go. It did the arithmetic for us. 0.0019289. Grams are the units on the top. Centimeters cubed are the units on the bottom. Now let's round it. This is simply, well, actually, this is a complex problem, right? You've got subtraction here. Notice this one goes out to the tenths column. This one goes out to the tenths column. So our answer should be known to the tenths column. So this one has 2 sig figs. The bottom one has 4 sig figs. 9.850. The 0 is significant because there's a decimal point, so that's 4. So our answer can only have 2. Remember, multiplication division can only have the number of sig figs as the measurement that has the fewest, so that would be 2. So that would be the first one, and that would be the second one. The number that comes after the 9 is less than 5, so we just truncate it. Now that's in decimal notation. There's nothing wrong with this answer in terms of decimal notation, but often they want to have it in scientific notation if it's a small number. So here's how you do that. If you have a number and you want to put in scientific notation is a number between 1 and 9 times 10 to the x, where x is a whole number. X can't be 1.7 or negative 3.4. It's got to be negative 1, negative 2, negative 3, positive 1, positive 2, positive 3. It's got to be a whole number, an integer value. So here's what you do. You move the decimal point the number of spaces it takes to get it so that you got a number that's between 1 and 9. So if I move it 3 spaces, I get 1.9. Well, that's between 1 and 9, right? 1.9 is between 1 and 9. So this would be 1.9 times 10. Now we just have to figure out what x is. If you move the decimal to the right, x is negative. If you move it to the left, x is positive. So since we moved it to the right, it's going to be negative. So negative 3. Okay? Grams per centimeter cubed. And there you go. 1.9 times 10 to the negative 3 grams per centimeter cubed, or 0.0019 grams per centimeter cubed.